Good morning everyone. Today we will discuss about pole placement controller for a DC motor. This is a part of 1 week online unique hands-on Sdp and control system design from a beginner to an expert Sdp 1.0. And this is the supplementary file for the lecture which has been discussed on day 3 July 22, 2020. And myself is P. Bharani Chandrakumar and I am an academic at Gmrit Institute of Technology. We'll revisit our DC motor model which we have discussed from the past couple of days. So we have seen how to obtain this DC motor model state space matrices, A matrix, B, C and D, and you can see that the order of the plant is 2. It is a second order system, and we have taken this model from, this is the source from the Michigan University website. And here the design specification is the settling time should be less than 0.06 seconds and overshoot should be less than 5% and 0 steady state error. This is the fundamental, this is the base code for the pole placement control design for a DC motor. These are the parameters which we have taken from the reference what we discussed in the earlier slide, J, B, K, R and L. And these are the ABCD matrices. The same we have seen in the day 2 and day 3 as well. And DC motor underscore SS equal to SS means state space model. So we are creating here the state space model of A, B, C and D. Since ABCD matrices are there, we are creating the DC motor state space model by using this command SS. SS is the state space. To design any pole placement controller, the first thing is we have to do the controllability test. So the controllability, while doing the controllability test, we have to ensure that the rank of the controllability matrix should be equal to the order of the system or should be equal to the number of states. So this is the system order equal to order of DC motors is. So as we know, it is a second order system, so and hence there is no need to do this one. But if the system is 100th order, 200th order, you cannot simply calculate by using hand or something. So this is for the system order. And the system rank of CTRB, this is the controllability matrix. For the controllability matrix, A and B are required. So if system order equal to system rank, that means if the rank of this controllability matrix equal to 2, then I can say that the plant is controllable, otherwise plant is uncontrollable in our case. If I run this one, the plant is controllable for our this particular plant. And for the pole placement controllers, we want the closed loop pole to be placed at -1000 and -2000. And this is the K underscore PPC. So this is the pole placement controller gain, and the place command will place the poles. The command place A comma B is already the plant dynamics, and P1 and P2 are the desired poles. So we are trying to place the closed loop poles at this desired location. So this command place or command occur, ACKER, will do the job. And once this gain has been obtained, then what we are trying to do is we are trying to plot the step response of the closed loop system. We are interested only in the first 0.05 seconds because we want the settling time to be less than 0.06 seconds. So that's why we have limited. So in the x-axis you will only see the time till 0.05, and 0.001 is the increment value. So if you want more finer one, you can take more more smaller this value, but it will take more time to plot the results. So syscl, this I am saying it is a closed loop system. So steady state, the state space of A minus BK. So this is now my new A matrix has become A minus BK into PPC, which we have already discussed in the class. The B, C and D matrix will be the same. And now this step command will plot the closed loop step response, and I am gridding it. And the title is step response with state feedback controller. Because why we are calling it a state feedback control? Because U equal to -K into X, all the states are required for this particular plant. We will run this one and we will see what is happening here. So the same thing you can copy and paste, which I have done here. This is the complete code. I will run only the part of the code until this itself, what we have seen here. As soon as I ran this code, so it is taking some time because we want the plot to be very smoother, and we have selected the plotting interval is 0.001. So the plant is controllable because it has satisfied our rank and order. And this is the one you can see that the thing in the first instant it looks very nice. Settling time is less than 0.005, and there is no overshoot and other things. But one thing one has to see here is this particular thing. It's supposed to settle at 1, but it is settling at 1.2 into 10 to the power of minus 6. That means it approximately very small, or you can treat it as 0 as well. If you want to see the characteristics, the specifications, right click and go to the characteristics, peak response. I will use all those things at one go: settling time, rise time, and the steady state error as well. So each of the things, if you hover your mouse and left click it, so it will show the corresponding specifications. So here you can see that the peak amplitude is 1 e minus 6, and the overshoot is 10 to the power of minus 14. That means it is almost 0. There is no overshoot here, 0 overshoot. But here you can see that instead of 1, it is settling at 1 e minus 6. That means approximately 100% is the steady state error. Because 1 e minus 6, that means 1 into 10 to the power of minus 6, which is very, very small. You can treat it as a 0. So this is 100% steady state error is there. Setting time is 0.00471 seconds, and the rise time is fine. So you can see that the settling time, you can see that settling time is good, overshoot is almost 0, which is good, but it doesn't have this steady state error is very large. So hence this design cannot be accepted. And the next thing is, what we have done here is we have gone for the pole placement controller with the integral action. We have seen in the integral action, so this is again from the class, you can refer the class notes. So what we are trying to do here is we are trying to get the augmented plant with the integral action, where the integral action will take care of the error of the error integral, whatever the error you are getting from the reference minus plant output. So what the error is getting integrated, and it is been multiplied with the corresponding gain to get a part of input. So this is the augmented plant, this is the augmented A matrix, B matrix, and BR, this is the reference one. You can see that the last element here also, if you remove this zeros and this particular element, it will be the same thing. We are augmenting with this C matrix here, just for the dimension satisfactory. We are considering zeros of 2, 1, and minus C has been augmented here, 0 has been augmented here, and this 1 is the new thing which has been augmented here, and this 0 along with the C. So the new augmented systems AB, AA, BA, BR, and CA and DA. And the third integral error pole, for the pole we have considered as minus 300. And then what I am doing here is KA, this is my new gain with the integral action, place of AA, BA, P1, P2, P3. Here only P1 and P2. The third is the integral new state has been introduced. The same thing I am plotting here, the closed loop AA minus BA into KA. This KA is a new pole, BR, CA, DA, and if I plot this one, you can just copy and paste this file. So what I will do here is I will plot now the second part. Yeah, so good thing here, you can see that it looks very much similar to the previous one, but the good thing here is it is going to 1. So the steady state error is 0 here in this case, which we'll see what is happening here. You can see that overshoot is 0, which is 10 to the power of minus 14, which is approximately 0, and settling time is 0.005, which is less than 0.006, our desired one, and the rise time is also very slow, 0.003, and steady state error, you can see that the steady state error is 0 because the final value is 1. So there is no, when the system reaches the steady state, there is no such error. So this is the way to do this one. So now this is by using the coding approach. Now if you want to do the similar thing in the Simulink thing and we want to see what is happening, so this is the summary, the two results what we have seen without integral action and with integral action. The main concern is the steady state of approximately 100% for without integral, whereas with integral is 0. So this, you know, our desired specifications has been satisfied with pole placement controller with integral action. And this is the pole placement controller design in the Simulink. So what I will directly show you these things, this plant. This is the plant, which is quite straightforward. So what is happening here is this is x dot. If you are integrating, you will be getting x here. So this signal here is a into x. This signal, if I assume this is a u, so b into u. Don't confuse with this u. U is the one which is going to this particular block. This is not exactly the control input, the u. The u nomenclature what you are seeing here is which is going inside this block. So here the x is coming, so a into x is the output. And here I assume that you know, if it is b, if it is u, so b into u. And this is my pole placement controller gain minus k into x. What we have seen, x is coming here, minus k into x, which is going here, and 1. So this is c into x, y equal to c into x. So the more important thing from where you will get this block is the gain block, which you might have already seen. You just type gain here, it will show you the various gains, or it will be in this math operation block. So you will get that one. But important thing to note here is that what selections you have to do here. So there are many, you know, there are 4 such options. You have to select matrix k into u, otherwise if you are selecting some vector or something, there will be some dimension issues. So this you can create it, this k, this a value, b value, a, b, c, and this k ppc. Since you already you have to run this particular whatever, you know, this particular code, then everything will be saved in the workspace. From the workspace it will be called. Now if I run this one, so once if I run this one, then you know, you should get the same results what we have obtained for the earlier one. Yeah, you can see that it is 1 into 10 to the power of minus 6, because this is 10 into 10 to the power minus 7. That means 1 into 10 to the power minus 6. It is the same thing without integral action. Now with integral action, this is the block diagram with integral action. So what we are doing here is, since this integral action is coming into the picture, there are the gain has 3 elements, the 2 elements for the plant and the 3rd element for this additional state whatever we have added, integral of error. So this is 3. So what we will do is, just I will run this one with the integral action. This is pretty much same. So this is x dot equal to a into x plus b into u. The u, how it is getting generated is, there are 2 components. One is coming from u equal to minus kx, the another is coming from minus k e. Actually this is e in the nomenclature, so k, the 3rd element of 3 into the integral of error. So again everything is the same. So you have to minus k of 3 you have to write, minus k of 1:2 you have to write, and this is b, this is a, and this is c matrix. If I run this one, you can see earlier it was 1 into 10 to the power minus 6. Now it is 1. It has gone to, so the steady state error is 0, and within the desired specification, the what results what we have seen here, what results what we have seen here, yeah, this one, the more or less the same results you are getting in the Simulink as well. Yeah, so the lesson is here, if you use the pole placement controller without integral, you can able to satisfy all the desired specification except the steady state error. So we already knew that to eliminate the steady state error, some integral action is required, and hence we have introduced the integral action for the error so that the error, if the error will go to 0, that means my reference and my output will be the same. So that's it from my side. Thank you very much. Thank you.